Hello everyone, myself Dr. Hitu Anand, postdoctoral fellow, Triple Department, SSN College of Engineering. My paper ID is GT2101, a convenient demand response layout for energy efficient residential prosumers. So, demand response is one of the smart grid technology by which residential consumers can take certain actions depending on signals and from the utility. So in the future, there is going to be a real-time pricing strategy, that is dynamic pricing, that is implemented in order to achieve certain performance improvement, such as peak load reduction by the utility in order to improve the system performance. So we have analyzed uh, the AC and DC load at the consumer end when there is a real-time pricing strategy implemented. Also, the residential consumers are becoming prosumers with the integration of photovoltaics, also called rooftop photovoltaic systems. So we have analyzed with the two metering strategies, net metering as well as gross metering. These two metering strategies are already under research and we are analyzing it into the Indian scenario of residential photovoltaic power generation. So this is the conventional or existing power generation where photovoltaic power is injected to the grid, and from the grid along the fuel based sources power is consumed by the residential consumers, predominantly AC loads, and energy meter is used. Now in the proposed gross metering layout, the power generated at the consumers, so consumers turn to prosumers, is converted using the inverter and it is injected to the grid with the help of smart meters. So the utility is able to measure the injected grid power and it is communicated to the consumers so that they can reduce the whatever incentive they can receive because of the power injection. That is the gross metered strategy. Here again, demand response uh, is convenient to an extent because the demand response is implemented using this communication for the AC load. But the DC load is also possible to be interrupted if the smart meters are disconnecting this power supply. So what we have identified this and we have solved it by actually injecting the power to the DC, that is called net metered strategy, by which the power generated is actually consumed for the DC loads because the DC loads are consumer electronics having low power values, so it can be easily utilized, and the excess power is obviously there is going to be excess power, so that power is sent to the grid. Government is addressing us to consume the power at the distribution side itself instead of sending it all the way to the grid in order to improve the efficiency. So this net metering is identified to be convenient. Further, this one is having demand response to the AC load. So note that DC load is not interrupted because whatever power generated is consumed here itself in the DC bus, and demand response is nothing but intentional curtailing is also possible. That means utility can actually turn off certain heavy loads if they want, depending on the system constraints. So this is a problem formulation where the first one represents energy consumption. This is the whatever we are following existing one, and this is net metering based energy consumption where the flat pricing minus of the injected power. This is gross metering, flat pricing minus of injected power. Here you have same tariff, whereas here for the injected power, net metering will have a higher tariff comparing to gross metering because net metering is a volatile pricing strategy. So here is another scenario where we are implementing demand response with the help of a battery storage system. So here we are not following any net metering or gross metering. Here we are analyzing only for the battery connected scenario where the DC power generated is stored in the battery and it is utilized in the DC bus, DC grid, so that whatever demand response is conveniently implemented by the utility. So we made an analysis. So this is the specification for each home having 3.780 kilowatts. Light load is 780 watts, and we have scaled it to 150 households. So the PV capacity is numerically scaled to 1.443 kilowatts. So each home is having 1.443 kilowatts of solar panel, and the conventional pricing tariff is 3.15 rupees per kilowatt hour. Net metering PV energy pricing is 4.97 because this is the volatile pricing, and whatever power each unit they are injecting to the grid will gain a 4.97 rupees per kilowatt hour, whereas in the gross metering PV injection 4 rupees only gained for each power unit of injection. Because gross metering is a contract based method and it is for 1 year maybe, or it is like contract, and whereas net metering is more dynamic, so only we are having a price fluctuation. In this case it is 4.97 rupees per kilowatt hour. So the peak demand is limited to 400 kilowatt, and peak pricing is when 400 kilowatt is crossed, you have a penalty of 5.5 rupees per kilowatt hour. So this is the light load profile we have taken. You can see here is the peak values happening here. So it is coming around 780 watts. So this is the power demand generation profile. So this is the power demand, total demand. This is the power load. This is the light load, and the total PV generation for particular day. So this is the photovoltaic generation for the day, and this is the pricing comparison. In this we can see for 24 hours the energy pricing for the total energy pricing is 23,000 something, and if you are using net metered photovoltaic generation, this is the generation, this is the injection, because net metering only remaining power is injected, and whereas gross metering the total power is injected. So the pricing due to net metering is 16,967.94 for that particular day, whereas gross metering is higher value 17,000 something. Whereas battery storage scenario, the pricing is going to be 18,584 because battery storage we are not injecting the power to the grid. So if you implement demand response, by demand response, the peak hours they have to take certain action in order to minimize the consumption. So we have demand response of net metered consumers, demand response for gross metered consumers, demand response for battery stored scenario, and demand response for battery stored with load shifting. So it is possible to shift the load. So in the initial case of net metering, 18,348. For gross metering, it is 18,663 greater than net metering, and the battery scenario it is 18,841, that is greater than gross metering, but it is far greater than net metering. So if you see load shifting with the battery, it is 18,584. It is greater than your net metering. That means net metering is far better than this battery stored scenario. So we have identified using net metering strategy instead of going for battery storage, it is possible to achieve performance and a convenient demand response for the residential prosumers. So these are the various load profiles, that is power in kilowatts, and this is the peak demand that we have followed, and gross metering is going to be the highest, and net metering because the power is injected. Not that we have storage scenario where demand response is implemented, so that we don't have uh, power at this above these 400 kilowatts. Demand response is achieved by this. So by conclusion, demand response with battery and load shifting is achieved by load clipping. Net metering infrastructure is identified to be beneficial for residential consumers, also called prosumers. So net metering price of 16,967.94, that is uh, identified to be lowest when comparing to the gross metering and the battery stored scenarios. So the metering strategy is identified to be economical comparing to the battery stored scenarios. So we have also noted by load shifting, we can achieve some kind of uh, energy savings, that is price savings, but net metering is identified to be performing very well. So there is no compromise is made on the comfort of the consumers by implementing demand response with the proposed layouts. So these are the some reference.